You are welcome to this class. So, we want to complete the last part of applications of differentiation, which is known as test of extremum value. So, you will recall that we have discussed uh, four concepts of definition regarding the extremum value of functions. These are global maximum, global minimum, global local maximum and local minimum, which we explain in the graph of this form. So we have referred a point like this as a local maximum, okay, and a point such as this as global minimum, and the point C here we have referred to it as global maximum because you will observe that there are two maximum, okay, but one is greater. So the one that is greater is we refer to it as the global, and the one that is lower but maximum is one that is called local. And again, we have said uh, those point D, though it is a minimum, but there is a minimum which is lower than this. So this becomes the global minimum, and this is the local minimum. And again, we have also explained a point of this form, okay, where after getting touching the turning point, instead of this line to come down, okay, it is increasing from the left of E. Immediately after E, okay, the line also increases. Okay, this what it means. This point E is neither a maximum nor a minimum. So these are what we have explained in our previous video. But today we want to look at how we can use the concept of differentiation to determine the shape of a function like this. Okay, and we'll start this by recalling the definition of a derivative of functions, and from there we'll come up with a method for determining whether a function is either maximum or minimum. So we want to recall that if f of x, that is the function f of x, is differentiable at the point A, then its derivative exists. And what we mean by this is that the derivative f prime of x is equal to the limit, sorry, at A is equal to the limit as x tends to A, f of x minus f of e divided by x minus a. Okay, so we recall this definition from our previous video. Okay, so this can be represented in the graph like this. If you have a curve and this point A is this, and the point X is another point A. Okay, so this point is referred to as f of x, and this point here is referred to as the f of a. Okay, so we'll see that here what is happening here is the total change in on the vertical axis, okay, divided by the change in the horizontal axis, and that is what is happening here. Okay, where this point is a fixed point. Okay, we are evaluating the slope at this point is a fixed point. Okay, while this x is any other point as we have it here. Now, suppose this x is also fixed. Okay, let's say this point is fixed, that it is not moving. Okay, just as this one is fixed, the terminal point here is also fixed. Okay, so let's say uh, instead of this graph, we now have a point which is fixed, and that point here which is also fixed. Okay, so here for the same graph, here we have f of b, and here we have f of a. So in this case, whenever we see f of x, we can replace it with f of b, and whenever we see uh, b, we can replace it with whenever we see x, we can replace it with b. Okay, so when using this notion to define this definition, what we are actually doing is a formula which we refer to as the mean value theorem. But that is not where we are going. We want to introduce the notion for determining the maximum, though that notion is one of the notion. Okay, so since we are dealing with a basic calculus, we don't want to move into that. Okay, so we actually want to deduce a term from here. Now we'll now reframe what we have here to develop a concept for determining the maximum and minimum of functions. Okay, so having grabbed this, okay, this function in this case, okay, we will now say this function is differentiable in an interval AB. Okay, and if this happen, okay, there will be a point in between this, okay, where we can use to bring a new notion, which I already call the mean value theory, but we'll not go to that in details. We only want to use that to develop another concept. So now, suppose f of x is differentiable on the interval a comma b. Okay, as we have it in the earlier graph we have here. So the interval a to b. Okay, and so what this means is that its derivative, that is the derivative of this f of x, okay, exists on that interval. Okay, or exists at any point excuse me. So if this function is differentiable on this interval, its derivative also exists at any point of the interval. Okay, so in this case, if we let x1 and x2 be any 2 points, in the interval AB, okay, accompanied with the fact that this x1 is less than x2. Okay, we are considering 2 points, okay, which are intermediate in the interval AB, and then this it is such that this x1 is strictly less than x2. Okay, so then So f of x is also differentiable, is differentiable on the subintervals, on the subinterval x1, x2. Okay, this is what we are saying. Let's just have a clue of what we are describing here. We have said this is the point A, B. Okay, the notion we have described here is 2 points x1 and x2. Okay, so you recall that we have said x1 is less than x2. So you just have to grab it here. So this is a curve, okay, which is defined originally on the interval AB, and we are considering two distinct points, which is S1 and S2, such that this x1 is less than S2. Of course, this also form a particular interval. Okay, so the last thing we note here is that this same f of x, if it is differentiable on this interval, okay, the same function is differentiable from this point to this point. And of course, if that happens, one can find the slope from the function in this interval. Okay, this point will be f of x2, and this point will be f of x1. Okay, if this happens, we can find the slope. Okay, you can find the slope such that if this happens, you can find the slope, and the slope will be there exists, then there exists, if this happens, there exists a point. Let's say C in the interval x1, x2, such that let's move this up. Okay, what we are saying here is that if f of s is differentiable between x1 and x2, there is a point, okay, C, and this point is in between x1 and x2. Okay, and such that this happens, the slope of this function at C, okay, will be equal to f of x1, f of x2 minus f of x1, and everything is over x2 minus x1. Okay, so we call that this formula is obtained from the original derivative formula. Okay, so where x1 and x2 are two distinct points, okay, and both of them are points in the interval a comma b. Okay, so this what we refer to as a mean value theorem. Okay, mean value theorem. We want to use this notion to bring about a concept. Okay, we call it, in fact, as mean value. Okay, when it is being discussed under a certain theorem, okay, we refer to it as the mean value. But this is the mean value, okay, deduced from the mean value theorem. Okay, so what do we need this for? Okay, so let's bring this graph in a more magnified form in order to explain some of the notions we have made. So we'll call that. So this C is a point also in the interval x1 to s2, but it can also be changed to any point. Okay, this is phase, okay, just 1 point, and it can also be changed to any point, okay, within the interval. This one is not movable, but this is movable within this x is in between x1 comma x2. Okay, is an intermediary point between x1 and so this is a variable, this x is a variable, this is a constant. So now I want to use the notion here. Now, if we have a graph of a function f of x, okay, suppose we have the graph which is of this form as we have rightly said, okay, so we'll be particular about x1 and x2 now, since we know both of them lies in a particular interval. Okay, so here we have said this is f of x1, and of course this f of x1 is it is can be traced to this point. The f of x2 also will be somewhere here. Okay, this f of x2, okay, but it's okay. So it is obvious that x1 is less than x2. Okay, and here from our computation, we'll see that f of x1 is also less than f of x2. Okay, or use the with equality. Okay, so if x1 and x2 are two distinct points in a particular interval, okay, and when we have a function which satisfies this condition, such a function, okay, will be an increasing function. But this is where we are going. If f of x1 is less than f of x2, okay, what it means is that the numerator here, that is this minus this, is positive. Of course, since x1 is less than x2, we know this is already positive, okay, because if we bring x1 to the side, okay, this means x2 minus x1 is positive. Okay, this also implies f of x2 minus f of x1 is also positive, okay, or non-negative. Okay, so if you bring this term in, okay, the numerator here for this graph is positive, the denominator is also positive. What it means is that if you have to compute this using the operation division here, f prime of x here is positive. Okay, what it means is that if this happens, the slope f prime of x is a positive number, and what it means is that uh, the function f of x is increasing in this case. As you can see, it is increasing. Okay. On the other hand, I'll soon bring this as a definition, but we are just explaining this here. Also, if you have a graph, okay, which behave this way, okay, and similarly, we have our this is now f of x1, and this is f of x2. Okay, so here we will observe that our f of x1 is now bigger than our f of x2. Okay, in a similar argument, x1 is less than x2. Okay, that is obvious. But here, if you say f of x2 minus f of x1, this should be negative. The reason is that f of x1 is more than f of x2. Okay, and if you have to consider that in terms of the numerator here, okay, we'll see that here f of x1 is greater or equal to this. And in this case, what this means is that the numerator here is a negative value. So if the numerator is a negative value and the denominator is a positive value, the division of a non-negative term divided by a positive term gives us negative. Okay, and because of that, the slope of that function is negative in this sense. Okay, and if the function is negative, what happens is this shape of a graph. Okay, it means it is decreasing. It is decreasing. Okay, so two things to note here. If this f of x2 is more than f of x1, what it means is that the graph is the slope is positive. And if the slope is positive, what it means is that the function f of x is increasing. Okay, and second notion we have noted here is that if f of x1 is more than f of x2, okay, the slope here is negative. And what it means is this behavior. Okay, it means the curve or the function is decreasing in this sense. Okay, so these two notions will state them as a definition, and then we'll use that concept, okay, to bring more terms, okay, into the lecture. I think this is taking. So two things now you want to note. So let f of x be a continuous function or in a given interval. In a given interval, okay, then one, okay, let's say one, f prime of x is positive. Okay, when f prime of x greater than 0, what it means is that the slope is positive. Okay, f prime of x greater than 0 implies f of x is increasing in the interval. Okay, so I'm referring to this as a sorry, let's redefine this. This is in a given interval I. In a given interval I. Okay, so then f prime of x greater than 0 implies uh, let's give it a complete English. Don't let us give you room for ambiguity here. Okay, this implies that f of x is increasing in the interval I. Okay, this is more appropriate. Okay, also 2, f prime of x is negative. Okay, when it's negative, okay, it means this will be less than 0. Implies that f of x is decreasing in the interval I. Okay, so these are two things we have stated there, okay, are deduced from the earlier concept we described using the graph. Okay, and then uh, this is how we know whether uh, this is how to determine the behavior of a curve when it is decreasing or decreasing. Okay, and then uh, let us consider a few examples of these. How do we know whether a function is decreasing in a particular interval? How do we know that they are decreasing in a particular interval? Okay, then we'll now further use this concept, okay, to tell how a function is either maximum or minimum. So let's consider an example here. So the example says determine the intervals Okay, so we want to use this to determine the interval at which this function is either increasing or decreasing. Okay, so in order to do this, the first thing is to note to get the critical point of this function. After which we will now, when we get the critical point, okay, critical points will tell us the boundary of the turning point of the curve here. Okay, and with that, we'll now check each of the interval, okay, where it is either increasing or decreasing. Okay, so that's a solution. Okay, so here a function this is given. Okay, so the critical point of this, as earlier prescribed in our earlier video. Okay, so find the slope of this function, which is this. Okay, then at c, at c, we have that f prime of c will be 2c minus 9 equals 0. Okay, so that c means the turning point here. Okay, as we have earlier described in the previous video. Okay, so when we substitute c into this, okay, at the critical point, okay, there is a theorem that says the slope at the critical point will be 0. Okay, so this implies this point c, okay, from the equation 2c minus 9 equals 0 will be equal to 9 divided by 2. Okay, which equally means 4 number 1 by 2 or 4.5. Okay, so let's have this line. Okay, suppose this is the real line. Okay, and there suppose this is 4.0 4.5 as reality. Okay, that is the point c. Okay, now this turning point, okay, as let us know where the critical point of this function lies. Okay, so that means we have been able to formulate two intervals from here. Okay, one is that from 4.5 downward, okay, we have a particular interval 4.5 4.5 to infinity. Okay, I also have a particular interval on this line, okay, from here downward. Okay, this means another interval negative infinity to 4.5. Okay, so this 4.5 has divided this line to two. Okay, we have this interval, we have this interval. So what we want to know here now is that we now have two intervals. We want to know where the curve of this function is increasing or decreasing in these two intervals. And how do we do that? Okay, the previous concept we just described can help us to do that. Okay, so since we know the slope, we know the slope of the function. This, okay, we know this. Now, from the left of the critical point, okay, the points that are on the left are from negative infinity to 4.5. Okay, we can now select any point here. Okay, any point that will take here, we'll substitute the point here. So if this is positive, we'll see it is increasing from the left. If this is negative, we'll see it is decreasing from the left. Okay, we'll do the same for you by picking one point and check whether the interval here is also increasing or decreasing. Okay, so now from the left of C, of course C is 4.5. From the left of C, the point there, I think we know that. Okay, one of them is 4. Okay, we just pick a number Okay, any other number of people here, you can do the same thing here. Okay, so you want to choose x equal to 4. That's from the left of the turning point. Okay, so using this, okay, when x is 4, this will be equal to 2 into 4 minus 9. And of course, this is 8 minus 9. Okay, and this is negative 1, which is less than 0. Okay, what this is telling us is that the slope of the curve x squared minus 9x plus 8 is negative from the left of the turning point. Okay, according to the concept we described earlier, if the slope is negative, okay, it means the curve is decreasing in this. Okay, so we can now look at this. Okay, what it means is that there is a curve which is coming this way. It is coming down. That is the meaning. It is coming down. Though we don't know but we know the curve is coming this way. Okay. Okay. Also, from the right of C, okay, let's choose an integer. Okay, for easy computation. Okay, choose x equal to 5. Okay. So again, therefore, f of 5 will be equal to 2 into 5 minus 9. Okay, and of course, this is 9 minus 10 minus 9, and this is 1. 1 is positive. Okay, and what this is telling us is that from the right of a 4.5, the curve is increasing. Okay, so this is how we now make the conclusion. From the left, which that is the interval negative infinity to 4.5, the curve x squared minus 9x plus 8 is decreasing. Okay, on the interval 4.5 to infinity, the curve is according to the judgment here is increasing. Okay, so let's put that down. Then let us use the notion to discuss the topic of the day. All right, so since f prime of x is a negative for all x. Okay, I said for all x in this, any x we choose will survive. Okay, we only choose one x. Okay, but any x will give us a negative slope here. Okay, so negative infinity to 4.5. Okay, then f of x equal to this is decreasing. Okay, is decreasing. Okay, meaning in this interval the function is decreasing. Okay, let's see on the interval. Okay, this is also allowed. Okay, also since f prime of x is positive for all x in the interval 4.5 to infinity, then the function f of x then the function f of x equal x squared minus 9x plus 8 is increasing. Okay, it's increasing on the interval 4.5 to infinity. Okay, so now we want to define the maximum and minimum test for extremal. Okay, so here we define three terms. Okay, so if f prime of x changes from positive to negative at c. Okay, that is, if you have a slope, okay, before getting to c it is positive, after c it is negative. Okay, what it means is that positive means it is going up, the slope is going up. Okay, little after the turning point is now coming down. Okay, this gives us a certain shape, and this shape is referred to as maximum. Then f of x has local maximum. Okay, as you can see, the function is going up, the slope of the function is going up. Little after the turning point c is now coming down. Okay, it's positive. Little after this is coming down. Okay, that's maximum. Okay, so if f prime of x changes from negative to positive at c, okay, then f of x has local minimum. Okay, you can also describe this as from the left of the turning point, it is negative, meaning it is decreasing. Okay, when it gets to the turning point, okay, it is now positive, that is increasing. Okay, what is happening there is as we said in our earlier video, okay, the plane of a valley. Okay, this will happen, and that is called minimum. Okay, so 3. So this case is a case of the neither maximum nor minimum. Okay, so if f1 of x is positive, so from both left and right, of C, that is, on the left of C it is positive, on the right of C it is also positive. Okay, that's the case we have described in our first graph. It is going up, little after the turning point, instead of it to come down. Okay, it maintains a certain horizontal form, then again it goes up back. Okay, so this notion is true, or if it's negative, or if f prime of x is negative, from both from left and right of C, okay, then f of x has neither, okay, in any of these two cases, okay, we see f of x has neither maximum nor minimum. Okay, so in our earlier video, we have described this, and that is what we refer to as the turning point of such a function. Okay, is what we refer to as the point of inflection. Okay, so let us consider a few examples here to using the notion of a positive, negative concept. Okay, to determine the behavior or the shape of a particular curve or curves, as the case may be. So let's see this example. Okay, if you have to find the okay, so I want to find the extremum value of this function. Okay, that is, want to know determine certain interval. Okay, at which we have the turning point or the critical value to be maximum or minimum. Okay, so the first thing is to determine the critical point, after which we now tell whether the critical point is either maximum or minimum, then we'll find the value as such point. Okay, so solution. So here we'll first of all uh, apply the theorem in our last video to get the critical point of this function. Okay, so now to get the critical point, okay, we first of all find the slope of this, and that is x squared, okay, minus 2x minus 3. Okay, so at the critical point, okay, where f prime of c equals 0, okay, so we have the slope, this c to be 0. Okay, so let's move this up. So this implies f prime of c is equal to c squared minus 2c minus 3 equals 0. So using the factorization method, this will be equal to c squared minus c plus 3c. Okay, so when we use the factorization, sorry, this will be positive, this will be negative. Okay, so this minus is give us negative 2c. Okay, so and this implies c into c plus 1, we'll group this into 2, and here negative 3 is common here, and that will be negative 3 c plus 1 equals 0. Again, c plus 1 is common here, so this becomes c plus 1 c negative 3 equals 0. Okay, so here either c plus 1 is 0 or c minus 1 is 0. Okay, and what this means is that we have got two critical points. So okay, we refer to the one here as c1, and then that of this is 3. Okay, so these are the two critical points that we have. Okay, So let us represent this in the graph and see what is actually happening. Okay, let's just first show it on the real line. Okay, so that we know some of the things that we have here. Okay, suppose this is the middle, which is 0, and then here we have -1. Okay, again, we have 3 somewhere here. Okay, assuming, all right, if this is the real line, we have got about 3 intervals here to talk about. The first interval is from the -infinity to -1. The next one is from here to here. That's from -1 to 3. And the third interval is 3 to infinity. Okay? So in each of these intervals, in each of these interval, we want to find where the curve, that is given is either increasing or decreasing, and we'll use that notion to tell whether to tell where the graph has maximum or minimum at the critical point. Okay, so let's do this. So here we have got to talk about few things here. So we know that for the slope, this, okay, for the slope, uh, at x equal to, or at c1 equal to -1. Okay, we choose two values. Okay, one value from the left of c1, and the other value from the right of c1. Okay, okay, so we'll use that to tell what is happening. So we'll do the same for the point 3. Okay, we choose two values. Okay, and we'll tell what is happening, the behavior of the graph on the left of 3 and the behavior on the right of 3. So now use that to judge the shape of the curve. Okay, so now as c equal to -1, okay, so from the left here, that is from this portion, let's pick a number to see what the behavior of this. Okay, so choose x equal to, let's pick an integer. Okay, a point very near to -1. Okay, that's the -2. Okay, so don't forget we are choosing the first point here to know what is actually happening for this. Okay, so f prime of -2 will be equal to -2 square minus 2 to -2 minus 3. Okay, this is 4, and this is also 4 minus 3. Okay, so this is 8 minus 3, that's 5. Okay, and this is positive. Okay, again, anything that is happening here also value the right of -1 is the same thing as the left of 3. Okay, so it is wise of us to pick a point here. Okay, okay, and that point will stand for both the left of this and the right of this. Okay, so again, from the middle here, let's choose um let's pick a point there. Let's say 0 for easy tax. Since 0 is there, so here f prime of 0 will be equal to this will be 0, 0, 0 square minus 3 to 0, negative. Okay, so this is negative. Okay, it means here it is positive and here it is negative. Okay, like we said, whatever holds there holds for the left of 3. Okay, so also at c2 equal 3, in this case we want to consider a choice from the right of S3. So let's pick a point. So let's choose x equal to 4. Okay, again here, f prime of 4 will be equal to 4 square. Okay, don't forget this is the formula we are using. Minus 2 into 4 minus 3. Okay, so this is 16 minus 8. 4 square is 16 minus 8, that is 8. 8 minus of 3, that is 5, which is also positive. Okay, so it is positive here, it is negative here, it is positive here. Okay, so let's do the calculation now. So now let's find the extremum value at C1 equal to -1. So here we have that f of C1 equal to f of -1 equal to 1 over 3 into -1. Okay, that is we are replacing x with -1. Okay, and this is -1 square minus 3 into -1 plus 1. Okay, so let's evaluate this and see what this gives. So we take the cube of this, multiply by this will be -1 over 3, and this is 1. Okay, multiply by this, so this is -1. So this is positive 3 plus 1. Okay, so this means 3 minus 1 over 3. Okay, so accordingly, if you find this, this is 8 over 3. Okay, so this means when the critical number is -1, the extreme value is 8 over 3. Also, at C2 equal to 3, for the second critical value, again we have f of C2 is equal to f of 3, and this will be equal to 1 over 3 into 3 cube minus 3 into, okay, 3, yes, -3 square minus 3 into 3 plus 1. Okay, so 3 cube is 27 divided by 3, that is 9. Okay, 3 square is 9. Okay, and 3 multiplied by 3 is 9, so -9 plus 1. Okay, so if we find this cancelled, and -9 plus 1 will be -8. Okay, so here we have got two extreme values. Let's now see how this look like on the graph, the one we stated there earlier. So now let's demonstrate this on the graph. Then we make the conclusion using the graph. Okay, so here the critical value as we have stated earlier, that C2 is -1, and here this will be 0, that's the origin. So let's say this is 1, 2, and this is the second critical number, which is 3. So you will recall that at -1, when C1 is -1, we have got our f of C1 to be 8 over 3. So if you locate that here, that is equivalent to 2.333 and then that should be somewhere around there. Okay, so 8 over 3. So let's do this out. So here is the point. Okay, again, when the second critical number is 3, f of 3 is given by -8. So let's say that is located somewhere around there. Again, second critical number meets here. Okay, so this is a second decimal value. Okay, so as we have got in the interval we stated earlier, from -infinity to -1, we have seen that the tangent line, okay, or the slope of that function is increasing, meaning the line is going. So when it gets to the extreme point here, okay, we have said from -1 to 3, it is decreasing, meaning it is coming to this point, okay, and from 3 to infinity again, we said the line is also increasing. So this is the shape of the function f of x equal to 1 over 3 x cubed minus x squared minus 3x plus 1. So here is the shape of it. Though this may not look exactly, but this is how the shape of that graph look like. Okay, and this is the coordinate. This point is the coordinate 3 comma -8, and this point is the coordinate, that is the two extreme value that we have got, -1 comma 8 over 3. Okay, so those are the two extreme points. So here it's obvious now that the function, now let's conclude now. The function f of x equal to 1 over 3x cubed minus x squared minus 3x plus 1 as local maximum, at this coordinate, okay, -1 comma 8 over 3, and as local minimum at 3 comma -8. Okay, so as you can see here, the maximum value here is -1 comma 8 over 3, and the minimum value is 3 comma -8. Okay, so this is how we use the first derivative test to determine the shape of a graph, okay, or to determine the maximum or minimum of a function. Okay, so let us also consider another example. Okay, this time we'll consider an example involving a transcendental function. Okay, so in order to uh, see how it looks there too. Okay, so example 2. Okay, this says we should find the extremum value of the function f of x equal to x minus exponential x. Okay, so again, we will apply the theorem for finding the critical number of a function like this, after which we will apply the first derivative test to check whether this is either maximum or minimum. Okay, so solution. So by applying the theorem, if you find the first derivative for this, this is 1 minus exponential x. So at the critical point C, f prime of C will be equal to 1 minus exponential C, and this will be equal to 0. Okay, so we'll call that at the critical point C, f prime of C will be 0. So if we relate this to with this, okay, this means whenever we see x, we put C. Okay, accordingly, this is what we have. Okay, so from this equation, this implies exponential C equal to 1. Okay, by taking the natural logarithm of both sides here, okay, so this implies that is taking natural logarithm, okay, of both sides, okay, so this becomes C, and the 1 here is 0. Okay, so the critical point of this function, of this function, is 0. So now we want to apply the first derivative test by looking for the signs of the derivative, this, okay, we pick a point from the left of the critical point to see how this performs there, whether it is positive or negative. We do the same thing for the negative part of the positive part of C, okay, to see the behavior. Now, so we know that the derivative of the given function is this, okay, so and then we want to consider 2 points, okay, one from the left of the C and one from the right of C. Okay, if we represent this using a line, you see this is C, okay, which is equal to 0. Okay, we have a point here which is -1. Okay, so it's wise for us to pick just a number here, okay, and a number here. So what we want to see is that we want to see whether this slope is either positive here or negative, and the same thing here too. Okay, so from the left of the turning point, we want to choose x to be -1. Okay, so when x is -1, f prime of 1 will be equal to f prime of -1 will be equal to 1 minus this, and this will be equal to this. Okay, so let's use a calculator to see what this gives. So this is 1 minus 0.679. That is, if you are approximating to 4 decimal, you will recall that this exponential is an irrational number, okay, which has a non-terminating and non-repeating decimals. So we are only approximating this to be 4. So when we divide this, okay, the value of this is 2.718, like that, okay, as we have it on the calculator. So we are approximating this to 4 decimals. So when we calculate this, this is 0.6321, okay, approximate also. Okay, we'll see that the slope here is positive when x is -1. Also, from the positive side, let us choose x to be 1. Again, we want to see the behavior of the slope when we have this. So this is a 1 minus exponential 1. Okay, accordingly, okay, using the same value for this, okay, this will be equal to, that is 2.718. Okay, this is a 1 minus 2.718. Okay, so this will be 1.718, so approximately 2. So they will see that this is negative because this is more than this. This gives us a negative number. Okay, so We are able to see that from the left of the critical point, okay, the slope is positive, meaning from here, this is the critical point, and which is zero. From here, it means the slope on the uh, left here is actually going up, though we haven't determined the extremum value, okay, and from the left, okay, we have seen that it is negative, meaning the slope is coming down, okay. So now let's know the value of the function on the vertical axis. So that will help us to know where this curve will pass through. Okay, so therefore the value or the maximum value not okay. So let's bring this up. Let's bring this up. So let's say at c equals 0, f of 0 will equal to 0 minus exponential 0. Okay, so this is a negative 1. Okay, now see therefore the function f of x equal to x minus exponential x as local maximum and its value is the coordinate 0, that's the turning point, okay, comma 1. Okay, so if you have to comma, okay, comma negative 1. Okay, so if you have to locate that on the graph, let's see how this actually behave. Okay, we can't get the true graph from here, but at least we are able to tell the shape of the curve. So we are told that this is where c equal to 0. Okay, okay. Of course, this is positive part. Okay, the extreme value is negative 1. Okay, and we are told that on the left of this uh, critical point, the curve is coming up. Okay, so it will pass through this point, and immediately after the critical point is coming down like this. Okay, so these are the curve look like. Okay, so this is just a picture of this, and the coordinate here is as we have it is the coordinate 0 comma negative 1. Okay, so here is the shape of this curve at the critical point. Okay, and it has a maximum value. Okay, so uh, this is it about the first derivative test for finding the maximum or minimum of a function of single valid variable. Okay, so now let us look at some exercises that one can lay once hand on after watching the video. So we find the extremum value. Okay, we are putting here S because uh, we want to consider a chaotic uh, function, so that we have about three extremum values. Okay, one of the exercises. Okay, so find the extremum values of the following. So 1, the function f of x equal to x plus 2 cos x. Okay, we have to determine that on the, okay, if x is lie between 0 and 2 pi. Okay, we have to find the extreme values of this function. Of course, we are doing this because of this cos x, which is transcendental, and there will be a lot of extreme values. Okay, so that's why we are restricting this to this interval. Okay, so 2, we are also uh, got to find the extreme values of this. Okay, as you can see, this is a quartic function, and the extreme values of this will be 3 on the real line.